the first thing, let's put the benzene concentration on there. Okay, so what do we have? We have 22% benzene. Okay, where is the first point on your diagram? It's 22% benzene and what? It's on the zero oxygen, right? So it's on the actual fuel axis. Okay, so that one is easy, 22% benzene. Okay, and the next thing I want you to do is draw the airline. Okay, and draw it from 0% fuel all the way down to your point where you have pure air that is 0% fuel. Okay, that is the airline. That is the line where you have the oxygen to nitrogen stoichiometry throughout the whole, okay? The oxygen to nitrogen concentration on that line, if you draw it from up here at 100% fuel all the way down to 79% nitrogen, 21% oxygen. Okay, that is your airline. Okay, so say for example that you had methane up here. So you were at 100% fuel. You had a compressed gas, right? You would be at 100% fuel. If you now let air into that mixture, you would follow this line here. You would decrease the fuel, and you would end up at pure air. Okay, so the easiest way to put that on there is go from zero oxygen, 100% fuel is probably better, down to 79% nitrogen, 21% oxygen. That's this point down here. Okay. The next thing is to put the lower and upper flammability limits on the graph. Okay, those 2 points, here's the important part, they're on the airline because those 2 limits are in air. Okay, so put those 2 points there. Okay, at 1.4% fuel and 7.1% fuel. Okay, and those were from table AB-1. Okay, those will be right there on your graph. Then we're going to put the lower and upper oxygen limits. Okay, those are now fuel in oxygen. Okay, so they would be on the zero nitrogen line. So they would be on this axis. This axis here is your zero nitrogen line. So your upper and so your lower oxygen limit is equal to the lower flammability limits. That's the approximation that we said. There are a few cases where you might find an experimental value for the lower oxygen limit, but it's usually pretty close. And you may not be able to draw it so that you can see a difference. It might be 1.4, 1.3, 1.2. But you put that's on this axis now, 0% nitrogen, 1.4% fuel. So you should draw a line up through the lower flammability limit all the way to the lower oxygen limit and keep going, because we're going to need that line to determine our flammability limits or our flammability zone. Okay, the next thing we're going to do is so put the oxygen, the upper oxygen limit, and just be careful so you don't put it at 45% fuel, 45% oxygen. Okay, the upper oxygen limit is fuel concentration in oxygen. So you wanna go 45% fuel, 45% on this axis and go straight across. Obviously, if you have fuel and oxygen only, 45% fuel means 55% oxygen. So everyone. Okay, you with me so far? Then what we're gonna do is connect the upper oxygen limit with the upper flammability limit, because that is gonna define part of our flammability zone. Okay, we also need a stoichiometric line. Okay, that one, we calculated the fuel concentration and the oxygen concentration. We're still on 0 nitrogen, right, at this, if we just put the point on there. So the point we need is 88.2% oxygen, or, so let's say 88% oxygen, 12% fuel. So that would be that point. So we only have oxygen and benzene at this point. Then we're gonna draw the line from there to 100% nitrogen. So in other words, on this line, that's why it's called stoichiometric line. On this line, the only thing that we're changing, we're adding nitrogen, but the benzene to oxygen constant ratio stays the same on that line. And then we need the limiting oxygen concentration line, and we determine that it's between 10.5 and 12%. So, right, if we take the experimental value 11.4, that's a line where we have the same oxygen concentration, right, throughout the whole. Right, we just draw the line of 11.4% oxygen. So oxygen is this axis, 11.4, and then we just draw a straight line down. Okay, and now here comes what we need to define the flammability zone. If we're asked for the flammability zone in air, right? Air, flammability zone in air, it's anything that's on this side. Right, the right side of the airline, right? Because to be on the other side, you would have to add oxygen, right, to the air, and that's not what we have in this point. This is going to leak out. We're going to have fuel leaking out into air. Okay, so what we're going to do to define what the flammability zone is, we have part of it here, but we need to know what it is on this side. What is the flammability zone? So what we're gonna do, we're gonna choose the point here where the best point in my opinion is where the limiting oxygen concentration intersects the LOL-LFL line. Okay, so we put a point there and connect those two. Now see, we have what our flammability zone in air is, that little triangle at the bottom. Okay, so as you can see, the flammability zone for benzene is actually not that large. If we compare this to hydrogen, for example, the lower flammability limits is actually higher, but the upper flammability limits is like 75 or something. Then you have a much larger zone. So we're going to look at a few different components so that you can see. Now the question was, right, what we have is benzene in the tank that's inerted with nitrogen. We are here. If we now let air into this tank, are we going to get, or let benzene leak out? Are we going to have a flammable mixture?
Probably not.
So how do we draw that on the diagram? So we start here, and what happens when we let air in, we're gonna draw a line from here to the pure air point, right? That's what we're gonna follow if we let air into that tank, and what happens? Yes, we're gonna have a flammable mixture, because we're going, that line that we just put on there, right here, it's going straight through the flammable zone. And you can see that we have to go to a very low benzene concentration to avoid this zone here, right? This is the zone we want to avoid at all costs, right? We do not, we want to be on the, either we want to be to the right of the limiting oxygen concentration, because then there isn't, no matter what the fuel concentration is, there isn't enough oxygen. Or you want to be below the lower flammability limit, because then there's not enough fuel to burn. Now, of course, that's a little bit of an issue, because at 1.4% benzene, that's not a whole lot of benzene, right? And if you're asked for the entire flammability diagram, or the entire flammability zone, that is the flammability zone in air plus the rest, whatever is confined within the LOL, LFL line at the bottom, right? Below that, the fuel concentration is too lean, it won't burn, and, right, if you're above the upper oxygen limit, or the line that connects, it's actually not a straight line from UOL down to this point here. And now you will see in some other problems that we're looking at, you're connecting the UOL with the LFL, and then you're connecting this line with this. It just happened that this problem looked like there's a straight line, okay? We're gonna look at some other ones where that is not true, where you might have, your UOL might be higher, but it goes down like that, and then you have a different slope. Okay, are you with me so far?
Since the flammability region in air is always going to be to the right of the airline, doesn't that mean that any leak is always going to pass through that flammability region?
For benzene, yes. Right, I mean, you can, it's only if you're down here, right? If you're down at a concentration of, I don't know, 2-3%, that you can actually avoid that triangle. So, but here is why it's important for you, because all flammability zones like this are going to be different, depending on what you're looking at. For other components, for example, I think methanol has a lower flammability limit of 7.4, like where the 7, you write something like that. Don't quote me on that one. But they have much higher lower flammability limits. So it's easier to avoid the flammability zone in that case, right? As long as you keep the concentration of fuel below that, right? But here's the key, right, in all of this, that we do need to avoid. It's very easy to have a flammable mixture, right? So you have to inert tanks, but you also have to be very careful. If you have a tank of benzene, for example, right, that's inerted, but you need to take it out of service, and you need to have welders come in and weld on it. You cannot just let air into that system. You have to drain it, pump in nitrogen until you're below a certain fuel concentration. Then you can let air in. And then of course you have to make sure that you let enough air in. If they're actually going to go into the tank and weld on it, you have to have air in there, because otherwise they're going to die from asphyxiation. If they don't die from the welding, I would never want to be a welder, I can tell you that. Right? Because you rely on other people as well. Right? There's been a lot of mistakes done, and we're going to see some CSB videos on that. Right? Hot work. is a very dangerous operation because you're relying on that someone else has cleared the area. Although you can, obviously you can take precautions. A welder welding on equipment that has been used for flammable liquids should have a flammable gas monitor on them, right? So that you know that there's flammable, that you might have a flammable mixture, right, when you're welding. So I took a lot of time, and I'm not sure if you know one has complained yet, but our TA is out of town, so I decided to try to cover, right, what I wanted to cover, and right, instead of having so we're going to continue doing problems, right, on Thursday. And we still have a little. The question is, should we work on? I did not grab another flammability diagram, but I want to do that on Thursday. Maybe we'll look at one of the CSB videos now. But so for the flammability diagram procedure, right, here's what we just did, but point by point. Draw the airline, put the LFL and UFL on the airline, then you put the limiting oxygen, the lower oxygen limit on your diagram and draw a line that goes across a straight line from LOL to LFL and out. Then if you're asked for the entire flammability zone, then you need to find the upper oxygen limit and mark that on the axis. And that needs to connect with the upper flammability limit, which is on the airline. Then you calculate the stoichiometric oxygen concentration or fuel concentration so that you can draw the stoichiometric line. You look at whatever limiting oxygen concentration you have and put that line on there. And then what marks your flammability diagram in air is that triangle between, right, the airline, lower flammability limit, upper flammability limit, and the point where LOC intersects either the stoichiometric line or the LOL-LFL line, okay? And really what I would like for you to do, right, is to choose the one that gives you the larger region, because obviously that would be safer, the safer of the two. Okay. Oops. Everyone, obviously, you'll have that, all of this, you know, and that's what we just did. It's important too, obviously, and then sometimes you don't have a pure component, so if you have a mixture, and obviously we have to be careful here, but most often, hopefully, you'll have a mixture of similar components, then you can calculate the lower flammability limits and upper flammability limits of the mixture. And you do similar to what we did for the time weighted average of the mixture, right? You look at those, you take the components, but it has to be the fraction of flammable on a combustible basis. So in other words, if you have nitrogen in your system, you ignore the nitrogen, right? And you look at what you have in terms of fuel and oxygen. And you calculate the fraction of flammable you have and divided by the flammability limit for each component. Then you will get something that's, right, approximation of these limits for the mixture. And you already know what the, right, the ones that you have listed in your book are at ambient conditions, right? So if you have other conditions that you're looking at, you have to use the equations that we saw, right, that we went through